always get asked this question, steel or concrete? And anyone that gives a precise answer, well, they're all wrong, because there's too many factors that determine whether it's concrete or steel. So what I want to give you today is a sort of world perspective of what's been happening around the world. And I'm not going to tell you which is better, but it certainly will tell you why we're using steel and why we're using concrete in buildings around the world. But the trends in the past 20 years, if you look at the top 100 tallest buildings in the world, there have been three big shifts that have been happening in the last 20, 30, 40 years. One is that before 80% of the world's tallest buildings were in North America, and now over 80% of the world's tallest buildings are in Asia and the Middle East. And that includes India. There's only one or two there, but that's going to increase. The next big shift, and this does affect steel, is the big shift is that early, before 1990, 10% of the world's tallest buildings were residential and mixed use, whereas the rest were office. And now, more than 60% of the 100 tallest buildings are residential. And what does that mean? Residential tends to be small spans. They tend to be, we want to minimise the floor-to-floor heights. And so that straight away has an impact on whether you use steel or concrete. I'm not saying which is the better answer, but it certainly does influence which way you go. And the third one is the massive shift from structural steel to concrete in tall buildings here. Before 1970, over 90% of the world's tallest buildings, the 100 tallest buildings, were structural steel primarily, and now over 95% of the tallest buildings in the world are concrete and composite. And we shouldn't forget that. There are many reasons for that. Well, why? A couple of things that I can think of is that concrete strengths, even in my career, have gone up from something like 40 megapascal to 140 megapascal. The country where I come from, in Australia, 140 megapascal is readily available, and I've used it for 60, 70, 80, 90-story buildings. And so this gives you a nice layman's diagram on this is what we needed 50, 60 years ago, the red column. Now we can get away with the green column. And composite, well, we've still got a smaller one, but I'm just saying relatively, where concrete is improving dramatically. And the second big trend in the world is advanced formwork systems. And we can have buildings that now climb up very, very quickly. The cores can quick. This particular building, the tallest building in Australia, which I was involved in, that core was going up at 3 days per floor, 6 days double floor. And that's why it's so far advanced. The reason why it's so far advanced is that because we want to get rid of that $1 million formwork, advanced formwork, get it off the site and get it onto the next building. And same with the perimeter system. There's only 20 workers on this project doing this infrastructure. The whole perimeter system, the formwork was jacked up on hydraulic lifts, and we're getting 4-day cycles, if not 3.5-day cycles. So they're the two trends. So our traditional composite slab, which traditionally is very, very quick, is not that much faster. We should be able to do it in 3 to 4 days. So that depends on a lot of factors such as craneage. We're going to get all those members up. So when we talk about steel, structural steel, as a fast construction, it's only going to be good as its weakest link, which includes fabrication, transportation, craneage, etc., etc. So, what is the trend? What's happening now? Before it was structural steel, well, now the trend is composite. This is what was happening 30, 40, 50 years ago, and one of the speakers in the other room just before lunch talked about the Twin Towers, how resilient it was against the events of 9/11. Why did the buildings stay up so long? We keep talking about why the buildings came down. I always ask myself, and I know the reason, because I know the structural system, but we should be asking the question, why it stayed up for 1 or 2 hours and let most of the people get out of the building. And it was a lot of robustness to the structure, but it was a pure structural steel. Empire State Building, 70 years ago, it was built in 1 year, 3 months. 90-story building. And why? Because there are lots of depression, lots of resources, lots of cheap labour, and so if you put your will to it, you can build things very, very quickly. So, the present 5 tallest buildings in the world, well, they're all composite, but dominated by concrete. And we shouldn't forget that, it's concrete. Essentially, Burj Khalifa is concrete. So I'm not trying to paint a bleak picture here, I'm just setting the scene. And what that means in terms of our steel industry, we need to address how to get more competitive. And we have to address all the parameters, because certainly the owners of these 5 buildings, they've selected concrete. And the reason why is it is more economical, no doubt about it. So I want to show you some examples of projects that my company and I have been involved in, and just to explain why we use steel in parts of the building. This particular project, I was a client's engineer. I wasn't the designer, but I was a client's representative. Dictated the way we want to go. It's called the CMA Tower in Riyadh, Saudi Arabia. And you can see the columns are going in and out to form a crystal shape. So as soon as the columns go in and out, and Newton's law, physics, the force has to go down, but the columns going in, there's going to be lateral forces. And the lateral forces are either tension or compression. Obviously, when it's tension, we need to use steel. And so there were 2 things, the columns were concrete-filled steel tube columns, and there were lots of structural steel in there in terms of horizontal elements that were pulling the columns in to make sure that they don't collapse. So you just give some vision there of large concrete-filled steel tube columns. And I'll give you a whole lecture on concrete-filled steel tube columns, because a concrete-filled steel tube column, the compressive strength of it is higher than the concrete strength of the concrete, plus the steel strength of the steel, because of the triaxial. And for the people that have done saw mechanics, you'll tend to understand why, but I'm not going to give you a lecture here now. But are very, very efficient, and certainly being applied in North America and Australia. Very, very impressive. It's great because you can progress the construction without the concrete in the tube for a certain distance, take the construction load, and you can fill the concrete, a steel tube with concrete, high-strength concrete, during a non-critical period, so that the building keeps progressing. This project, another reason why we want to use steel here, well, it's just that impossible to use concrete. A typical Zaha Hadid design, and for people that don't know, Zaha Hadid unfortunately passed away just last year. She never likes vertical columns and straight elements. That's a bit of a challenge for our structural engineers. But this was the project, and what you see there is the structural skeleton. It is structural. There are no perimeter columns. There's a concrete core in the middle. Externally, what you see is the structure. So it's almost impossible to have any other material except steel. And why have we got such a complex tower? Because it's going to be a very, very expensive tower. If anyone tries to tell me it's going to be a cheap tower or an affordable tower, obviously you're joking. But there's something that's based over here that generates a lot of money. It's called a casino. And it's a hotel above a casino, and this thing, the cost is peanuts compared with the profit that they make out of the casino to fund this hotel. And so, hence the reason why it's so complex. It's going to be an architectural feature, and it's going to dominate the Macau skylines. The only reason we can do this now, and hence why we can be creative with our structural steel, is because we've got digital engineering. From geometry, we can convert to final element models within the joints and analyze it all by the press of a button as long as we program it. We couldn't do this. It would be almost impossible to design this 10, 20 years ago. We can do this now because of digital engineering. I was going to, I'm lying, just see if I can show a video. It's not going to work, I don't think. Yes, it is. So this particular project, so you get the geometry from the architect, and automatically we can get from the geometry using Grasshopper and Rhino into a final element model, and then analyze it for all the different load classes at the click of a button. So even if the geometry changed, we can automate the whole process, which only takes a few hours to run, to basically analyze all the joints. So just some pictures of the complexity, and just shows you the versatility of structural steel. Because we can define it now through digital engineering, it's so easy for the fabricator, so easy for the structural engineer, because we can define it through digital engineering. The National Bank of Kuwait, that's another interesting project, very, very expensive. The reason why it's very expensive because it's the headquarters for the National Bank, and they can afford to pay a little bit of penalty to market their building as that iconic structure that symbolises the bank. And this whole building, for the structural engineers, is highly eccentric. So the building wants to tilt over compared to the stiffness compared to the centre of mass. And of course it's concrete, the core is concrete, so it wants to continue to creep. Moving over time, and so we needed to have structural steel to minimise that tilt and to predetermine some presets. So we tilt the building the other way, so over 30 years it will not straighten, but it will tilt the other way, but we're compensating half of the deflections. So quite complex, but we had to use structural steel to minimise that tilt. Because the columns are curving, obviously push-pull forces, when it's curving downwards, you've got tensions on the slab, and so the whole thing, the outer plane forces were all taken by structural steel within the floor frame. And so structural steel was the only answer. There was no other option. Just give you some more images of the floor plate, composite with the steel tube columns. So everything is structural steel except for the floor slab and the concrete core. Some more images. It's almost, in fact, this is about 1.5 years out of date now. The building is almost topped off. The next project, very quickly, is a project that I was involved in nearly 30, 40 years ago, 35 years ago. It's called Market City. And I only got one slide here, but why did we use structural steel here? The reason why we had structural steel is that it's a very complex project. If I go to the previous slide, there's a market, movie theatres, shopping centre, vegetable market, fish market, meat market, in the basement areas. Very, very complex, and then the building on top of that. And so we needed to build this very quickly. These are the days when the interest rates in Australia were 18%, and the developer wanted to get this built as quick as possible. So we wanted to get off the foundations, steel tube columns, quickly up, and so you can see the concrete core is shooting up, so they merrily start building, virtually we go 20 stories above the floor, and we want to get a working platform where you start your typical floors. So there's 3 construction funds, one right at the top, one in the middle, and there are 3, and one at the base. Theoretically, everything gets finished on the same day. And so the whole building was completed in virtually 2 years. Whereas you started from the base and worked your way up in 3 to 4 years. Once again, only possible because of structural steel. That was the only answer. Okay, getting pushed here, 5 minutes. Okay, Akil 1 kilometre high tower. This is a project in Dubai that I think I've got the title there, Victim of Global Financial Crisis. It didn't get built, but that's only half truth. The foundations did get built. About 170 million US dollars worth of foundation is buried under the sand in Dubai. And I designed the foundations, I'm proud of that. 100 metres concrete structure again. However, lots of steel. And just some of the examples. Because the spans between the mega columns are 22 metres, we had internal columns in between the 2 big black blobs, and that had to get transferred every zone where you've got this band beam here. And at that band we had steel truss. And the reason why it's steel is that the concrete just kept on going, and the steel elements were built in non-critical periods. So lots of structural steel there. Secondly, when the wind blows, there were 4 quadrants and they were connected by these link beams. And those link beams had to be in steel, simply because we're trying to transfer 200,000 kilonewtons. If you don't understand what 200,000 kilonewtons is, it's equal to a small ship. Now the force that goes across that. And concrete, well, the shear forces are so excessive that we have to have steel. And so tons and tons of steel and all those link beams. The top feature, even though it looks small, that top feature, the roof feature, is the same weight as the Eiffel Tower and virtually at the same height as the Eiffel Tower. It's 1 kilometre high. You can see top 200 to 300 metres was structural steel. And so once again, structural steel is the only answer because of the geometry and will minimise the weight. And then lastly on the McKeel Tower is that in these zones there's plant roots that span across that whole central void, 3 or 4 stories of it, and that had to be structural steel. And that was dictated by not weight, or it was all to do with buildability. How do you build that platform up in the air? So the next diagram shows you that the whole structural steel framework was all constructed at the base, and then it was jacked up, a bit like the previous slide. Top-down construction, the whole thing was built in the base, and it was all jacked up to build those platforms. The future. I've sort of painted a bleak picture for steel, but you can see that we do have lots of steel application. But where are we heading? Well, we go back to Henry Ford, building your cars, and where one person does one activity, but does a damn good job of that one activity. Becomes very, very good at it. And that's where we're heading when it comes to buildings. We're going to be building elements in the factory, and they're just going to be installed very, very quickly. And this is going to happen in India. That's my vision. It has to happen in India because we seriously need lots of buildings at an affordable price, and it has to be flexible, it has to be quality. People are going to be after quality, and so I think it's going to be built in a factory, and it's still going to be plonked on site, and it's going to be primarily steel because of its weight, versatility, and flexibility of manufacturing. In Melbourne, where I come from, the questions are being asked by particular companies and research that we want to build 90% faster, 100% of the components can be reused, sustainability, 80% reduction in traffic use, 70% reduction in transport, site, labour. How do we do this? It all comes to prefabricated buildings. This is a real building in central Melbourne, which has got hardly any access to one of these small laneways. It's not a big building, but it was built in virtually 2 to 3 months. 2 months. And that's where we're heading. Primarily, it's going to be structural steel. So, the last slide. Just have a look for 1 minute. Because this is where we're heading. This is not a 10-story building. China, I think it was a 30, 40-story building, and they're already doing a 150-story building. And this is where it's all heading. And I'm sure this sort of technology is going to come into India in the next 10, 20 years. So this obviously there's a lot of R&D that's gone behind this building. So even though it was built in I think 3-4 months, they spent billions of dollars, but it's the R&D, the research going into where the future is. And this is where I think it's going to be heading in India to meet the demands of 400 to 500 million people that are going to move from rural to urban in India in the next 30, 40 years due to that migration from rural to urban and due to natural population growth. So I expect that steel is going to be the answer, certainly going to have a major play in the answer to meet the demands of urbanisation in China and India, and hence the reason why we are here, I think, and why some of the steel companies are going to be investing a lot of money, and certainly should be investing a lot more money to compete with concrete, because concrete are going to be doing the same research in terms of meeting these demands. So I think that's it. Thank you very much.